Question 5, the Diels-Alder orbital question. Now, this is a famous version of the reaction, which is why I wanted to see it. There's a context here that's important. As it turns out, I didn't mention that the concept of frontier orbitals and HOMO and LUMO interaction actually won a different Nobel Prize for R.B. Woodward, who was also at Harvard at the time. So it was a very interesting time and place for intellectual development in chemistry, particularly organic. All right, but what happens here is we tend to get sidetracked by the size of what's going on. So specifically, we only really care about the Diels-Alder part, so we're really only concerning ourselves with this. Now, specifically, part 2 of the question says you can kind of ignore what happens on the diene. The electron withdrawing groups on the dienophile are the important part. So let's go and have a look at the orbital picture first. So for simplicity, just looking at the orbitals, we can behave as if it's just this, because all Diels-Alders come down to the same 6 orbitals, and then the modifications happen because of the groups around them. But as far as what's overlapping and why, we can look at this as very simple. So I'm just going to basically take the cyclic diene and look at the orbitals as if they're just a straight line for drawing simplicity. So there are 4 p orbitals, which means there are 4 molecular orbitals involved. There are 4 molecular orbitals involved here. So again, we're drawing these as if they're atomic orbitals. It makes things a little simpler to draw. The molecular orbital is a little bit more complex drawing-wise. And of course, my art skills leave a lot to be desired, so you can look at the same diagram in your book. Within that, the non-bonding line is dead center. Below that, we have 2 bonding orbitals, each of which can hold 2 electrons, and we have 2 antibonding orbitals above that line, which can't, or which can also hold 2 electrons, but don't in the ground state. So we note these as psi1 through 4, and the way we look at them is by shading in the orbitals so that we can say that in the lowest energy case, psi1, there are no interruptions in the flow of electrons. The orbitals are all in the same phase, meaning the shading parts are turning in the same direction. And we're going to get multiple interruptions in that flow as we go upward. So here, the lowest one, we have basically things behaving as if they're one large functional group, and that's what basically happens in a lot of reactions. We see a 4 pi electron system. Conceptually, we can think about the second one as basically being 2 separate pi bonds. It's not really what it is, but you can see that at least in your mind, there's still 2 pi bonds worth of overlap here. So I have one on the left and one on the right, shaded, phased differently. As we get to antibonding, though, we no longer have the ability to draw anything that resembles 2 different pi bonds. We're going to have too many interruptions in the flow of electrons. So we can basically say something like this. So I can still see one clear pi bond on the left. I don't have that on the right. And then the extreme case, the top has no uninterrupted flow at all between any 2 atoms. So generally, we're going to work with the ones on either side of the bonding line. These are the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And we're going to have the same picture for the alkene, but it's much simpler. So it only has 2 orbitals to deal with, so it only has 2 p orbitals to begin with, so it only produces 2 pi molecular orbitals, one with overlap. This is our pi orbital, and one without. This is the antibonding or pi star orbital. We don't number these because there's no point. There's only 2 of them, one good, one bad, one bonding, one anti. And this y-axis here is the energy axis. So our neutral point, the dotted line that goes to the middle of both, if I could draw a straight line, is the non-bonding axis where we would find all the original atomic orbitals before there was a pi bond at all. So again, these are the highest occupied and lowest unoccupied orbitals for the alkene. So generally speaking, to reactants, one is going to be reacting via the highest occupied orbital, the other via the lowest unoccupied orbital. So I have 2 possibilities. I have this possibility of this orbital and this one as my interaction, or I have this possibility. If we could ignore, or if we're just talking about the case where there's no substituents on the diene and the dienophile, we have no preference. They're identical in energy. The antibonding orbitals are exactly the same distance above the non-bonding line as the bonding orbitals are below it. So there's no difference in energy between what I have in rectangles versus what I have in circles here. They're identical. The difference happens when we start attaching substituents, and that was part B of the question. What I said was what's on the diene we could ignore. But the electron withdrawing groups on the dienophile are problematic. They do have an effect. What happens in that case is when you have an electron withdrawing group, it drops the energy of the entire orbital picture for the alkene. So what would happen is this entire part of the puzzle for the alkene would shift downward in energy. So here we're looking at a difference between HOMO and LUMO. It doesn't matter which pair I choose. But if I take the other set, if I take the look at what happens so what's happening is I put an electron withdrawing group on here is something like this. So now there's a big difference between, I'm sorry, it took the text of one with it. It took LUMO with it here. Now there's a much bigger difference between the ones I had circled, the highest occupied orbital for the alkene and the lowest unoccupied for the diene, versus these two that I have in squares relatively close together now. It also took the non-bonding line. Sorry about that. Motion is not Windows Journal's strong point here, so. So this is now my preferred combination. Those are closer in energy and therefore more likely to overlap. So that's the consequence of adding an electron withdrawing group. I realized I never drew the shading in on this. It's the consequence of adding an electron withdrawing group to the dienophile. It drops the energy of the entire system, and therefore one pair of orbitals is now closer in energy than the other pair. So we now have a preference as to which orbital is useful for which.